Hello, so this is the project submission for Team Anarchy, our energy monitor. So we built a anomaly detection model that would be able to look at energy efficiency across the OSU campus and bring back anomaly scores based on the energy consumption of the certain buildings. However, we didn't just stop there. We also went on to build investment priorities models, a priority portfolio comparison to show how each building compares to the campus average, and a consensus ranking if you just wanted to rank buildings by averaging multiple independent measures, just for flexibility for decision makers. And of course, we have multiple features ranging from electricity all the way to even oil if you want to go into it. So for an example, let's just look at the Ohio Union, a building we're all familiar with. So as you can see here, we've got electricity and heat as significant measures. And despite being such a large building, we've actually got a relatively normal energy cycle. However, if you look at the heat section, it's actually a bit worse than what we expected, making it more inefficient. And as such, the anomaly score has signaled us that we should think about it a bit more. And of course, we break it down by looking at the excess ratio, how much more energy this building uses, how much often the building uses more energy, whether it's very consistent, or moving on, and again, an anomaly score. But we also built investment impacts just in case, like a large building like the Ohio Union with lots of people going in and out, maybe you'd want to invest in it more. And again, for explainability, we put in our data as well as method comparison ratings. But just in case, decision makers don't want to go through this entire process, they can definitely go to our chatbot. And first off, they could just compile graphs for business presentations or whatever. So for example, here we're going to show the top 10 buildings by total electricity consumption in September 2025, and then visualize those as a bar chart for the consumption values. And so in real time, it will actually build you that graph and allow you to explore further. And as you can see, it's just built it. And from there, the OSU electric substation looks to be the most inefficient building on campus, and the veterinary medical center is the 10th most. But models always have to grow. So we decided that we'd build an upload data feature for the future, as we only got 2 months worth of data. As such, you can add a new meter data, new weather data, or new building data, just in case renovations occur. And especially for weather, because it's always a hassle, we built an API that would be able to do it. So for example, just the start of the year to like today maybe, you can fetch data, and if you give it a second, it will actually fetch that data for you and you can submit it. And then we'll move on to the details of the models. We started with about 1.5 million rows of raw meter data. A 7-step pipeline removed null keys, dead sensors, and outlier readings, retaining 93% of the data across all 5 utilities. As you can see, most rows are lost at step 6, where we drop completely dead meters. Gas retains 97.5% of its data, while steam is most affected at 88%. Overall, a rather clean and reliable dataset. We trained XGBoost across all 5 utilities using 25 input features: weather, building metadata, temporal indicators, and engineered lag and rolling statistics. The target is energy per square foot. Same hyperparameters are present across all utilities. 4 of 5 utilities achieved R squared above 0.92, but gas was only 0.65, too noisy for a tree-based model. That motivated us to build a dedicated gas model. As such, we designed a dual-branch LSTM, or long short-term memory. One branch processes 28 temporal features, another embeds building metadata. They fuse into a prediction head. Trained for 33 minutes on a Tesla T4, R squared jumped from 0.65 to 0.97. We tested 4 architectures on gas. LSTM won on accuracy at 0.97. XGBoost was fastest but least accurate. The takeaway: gas has strong temporal patterns that only sequential models can capture.